Hello and welcome to YMT215 Logic Circuits. This is the second chapter, number systems, operations and codes. This is the first part of the chapter. We'll cover these 5 basic topics: the decimal number system, the binary number system, decimal to binary conversion, binary arithmetic, complements of binary numbers. So basically this is the first part. The chapter is a bit long, but I'm dividing it into maybe 4 parts for the time being. Okay, initially we speak about decimal number. You guys are very familiar with decimal system. We studied it in primary school. However, we will try to approach it in a different way. For the decimal system, we have 10 digits from 0 to 9. So we go from 0 to 1, 2, 3 until 9. Then we run out of digits. So what happens? We start composing 2-digit number. So a 2-digit number is a number that has a different weight. So we have the units, the tens in that case. Why tens? Because it's decimal, composed of these decimal digits that we have from 0 to 9. All right. So this is the idea, and why we are explaining about this, because it benefits us later on in binary system. The same concept is applied in binary systems, and that's why I'm explaining it now. Okay, so we consider those as digits in the decimal system, and they are recognized by their weights. Weights means what? This one in the unit side, so its positional weight has a multiplication of 10 to power 0. 10 to power 0, anything to power 0, except 0 of course, is 1, so 10 to power 0, that's 1, 3 times 1. This is its positional weight and value. And for this one, its positional weight is 2 times 10 to power 1. And that is exactly the composition of 20 in this case. The further we go to the left side, the higher the positional weight will be. And we will see it in a while. If we sum up these two, then we find the decimal number result. So 2 times its positional weight, 2 times 10, sorry, 10 to power 1 is 10, 20 plus 3 times 10 to power 0, that's 1, so 20 plus 3, that's exactly 23, and that's how we compose numbers in decimal system. As I said, you may wonder, okay, why are you telling us about these basic things? They are a base for what will come soon. So the positional weight for the integer values of a decimal number will increase while we are going to the left side. So they start by 10 to 0 or 10 to power 0, then 10 to power 1, and so on. The exact opposite of this happens when we have a decimal point or a mantissa. In this case, the positional weight decreases. It doesn't start by 0 because it's included in the integer part of the decimal number. It goes from 10 to minus 1 or 1 over 10, and it goes until the last digit after the mantissa. Okay? So this is the idea. I'll give you a few examples. Now look at this simple example. If you want to represent it, if you want to represent this one as a sum of values of each digit, the value of 7 is 7 here, of this number. 7 times 10 to power 0, or 7 actually. And the value of 4 in this representation, I say not 4 by itself, 4 is 4. It doesn't change, but in this representation, it's actually 4 times 10 to power 1, or 40. So it's 40 plus 7. That's the exact representation. Let's take another number with a decimal point. Let's look at this number, 568.23. In order for us to convert this number to its positional weight, or actually to the weights of its own digits, we need to consider 2 parts. One with this mantissa, the one after the decimal point, and the integer part, the one left to the left of the decimal point. So this is easy, we are familiar with it. 5 times 10 to power 2 plus 6 times 10 to power 1 plus 8 times 10 to power 0, or actually plus 8 directly, because 10 to power 0 is 1. Now the other part is actually new to us in this case. 2 times its positional weight, 10 to minus 1, plus 3 times 10 to minus 2. If you sum up all those in basic mathematics, you will get the final value here. Now those are easy. 5 times 100, that's 500. 6 times 10, that's 60. 8 times 10 to the power 0 is 1. So these are exactly 568. Now look at this. When we divide 2 over 10, that's 0.2. And then if we divide 3 over 100, that's 0.03. So sum them up, you will come up with this value. As I said, these are basic things, but that's how the machine understands it, and that is how we introduce the binary system. The binary system actually is a system composed of 2 digits. Now, earlier we said about the decimal system, we have 10 digits, from 0 to 9. Now, 2 digits, what could be these 2 digits? 0 and 1. Okay? 0 and 1. Why? Because we don't have any other. 0, 1, finished. The count is finished, then we have to compose 2-digit number. If the 2-digit number is finished, we have to compose 3-digit number. Like when 99, we reach to 99 in decimal, we have to create 100 or 100 in decimal. We call that 100 in decimal. So this is the idea. How we count? We count simply. We start by 0, then 1. Our digits are finished. Then what we do is we compose 2-digit number. So it will be 10. Not 10. We don't call it 10 in binary. We call it 10. So 10. The next count would be 1, 1. 0 will change to 1. Now we run out of digits. So what will happen? We have to compose a 3-digit binary number, 100, and you move on. You start from the leftmost, and we will give it a value, a name, a specific name, and keep on increasing and changing these numbers. What is it useful for? What is this binary number or system is useful for? It is actually the base of all the computing machinery that we have now. Why? The computer is easy for the computer to understand. There is no logic 1, logic 0, or there is a value, there is no value. That is exactly how we run our computers. Otherwise, it would be extremely complicated for us to represent so many things to the computer. But with digital systems, 0, 1, series of ones and zeros, that's really easy to store and manipulate. So we convert everything to our machine in terms of a binary system. How can we count? Yes, we can count with it, but we need to represent it in different ways by decoding it, and we will see how. All right, so we spoke about counting. First 0, 1, then after that we run out of digits, so it will be 10, then 1, 0 will change to 1, then we run out again of digits, so we have to go to 100 and move on. If you run out of digits, 111, then you have to compose a new, that means 4-digit number, 1000. This is the idea, and you start from here counting. That means 100, the next one will be 101, the next one, this one will come back to its state 0, and this one will change, so 110, the next one will be 111. Okay, you will get used to it slowly, because all our actually semester or course would be based on those. All right, so how can we count decimal numbers, or what is the limit, or how can I know how many digits I need in binary system to represent a decimal number? We have a simple equation to do that. You need to know the number of digits, how many digits you need to represent a certain decimal number. So if you are going to count from, let's say, from 0 to, let's say, 7, for example, 7 here, how many digits do you need? If you take this 1 to the left side, so 7 plus 1, that's 8. So 8 equals to 2 to power n. So 8, we can decompose it to 2 to power 3. So 2 to power 3 equals to 2 to power n. Bases are equal, so the powers should be equal in this case. 3 equals to n, or n equals to 3. So 3 digits, or by using 3 digits, we can count up to 7 inclusive. Means 0, 0, 0 from 0 to 1, 2, 3 until 7 inclusive in that case. Let's say we make it the other way around. Let's say by 2 binary digits, how many decimal numbers can I count? 2 to power 2, that's 4, minus 1, that's 3, so we can count from 0 to 3. And it goes on. If you put 4 here, you will count from 0 to 2 to power n 4, 16, 2 to power 4, that's 16, minus 1, 15, so you will count from 0 to 15 in decimal. So this is 4 digit. You can count from 0 to 15, and that's how it is counted. We start all zeros exactly like the decimal, then all zeros except the last digit, and you move on. So this is actually a rhythm. We will explain about it later on, how when we design counters in later chapters, not now. Okay? Do you need to memorize this? Never. You are not required to memorize any. You are required to understand the rhythm. They understand the change. So how do we count 0, then 1? Those zeros to the left side do not matter. For the time being, they don't matter. Okay? So 0, 1, we run out of digits. We have 1, 0, then 1, 1. We run out of digits. 1, 0, 0, then 1, 0, 1, and so on. This is how it is done. I explain about those. Okay? The way we explain about the decimal system, we should explain also about the binary system. We have positional weight, the rightmost bit. Now, we explained about this before. This, like here, this is the rightmost bit. This is a bit. 0 or 1 is a bit. It could be 0, it could be 1. Now, for the timing, this is 0. So this is what we call least significant bit. The bit with the least weight. The weight here is 2 to 0. Now our base is not 10, it is binary system. Our base is 2. So 2 to 0. 2 to 0 is 1. So the positional weight is multiplied by 1, exactly like 10 to 0 in decimal. Here is binary, 2 to 0. Right, the next one is 2 to 1. So whatever here will be in the conversion to decimal multiplied by 2 to 1. Here 2 to 2. Or 2 to power 3. In short, I say 2 to 2, that means 2 to power 2. 2 to power 3 as a positional weight, and the more or the higher you go, the more positional weight will be similar to decimal system, but the base is in 2, base 2. Alright, so this is the least significant. The highest bit, which is the leftmost bit, we call it the most significant, MSB. This is called the most significant bit, and this is the least significant bit. So MSB and LSB, remember those, we will use them a lot, okay? And they determine the size of the binary number, of course, the weight of, or positional weight of the bits. Now, similar to what we explained in decimal systems, if we have a binary number with a decimal point, which is possible, we have to go in the reverse with the positional weight. Here we start 2 to 0, 2 to 1, and it increases while we go left further. Here, what happens? We start by 2 to minus 1, and it decreases while we go to the right further. Okay? So the further we go to the right, the more it decreases the power. Okay? And that's how we represent binary numbers with actually binary points. We don't call decimal. Decimal point, when we call it decimal point, it's in the decimal system, but in binary we call it binary point. Okay? Very similar to the decimal system. Now, in order for us to convert between systems, we need to know the weights. What does it mean of weights? I just explained about it a while ago. The first digit, or you can say the least significant digit, it takes the weight of 2 to 0, that's 1 in decimal. The next one takes 2 to 1, that's 2, 2 to 2, 4, 2 to 3, 8, 2 to 4, 16, 32, 64, and so on. Try to remember those, because they will come across with us a lot. Try to remember them. They are not really hard. Actually, you double each time, you double the number. Each time you double the number. So 1, double it, 2, double 2, 4, double 4, 8, double 8, 16, and so on. You keep on moving. Okay, this is the idea. And the reverse of the process exactly, if we go to the right of the binary point. So we divide by 2, we do not double, we halve. So 1 over 2, that's 0.5, 1 over 2 multiplied by 2, or 1 over 4, that's 0.25, and so on. These are helpful with if we have a question about conversion between binary and decimal, or vice versa. Okay, so binary to decimal conversion, or BDC, in this case, what we need to do is we have a binary number and we need to convert it to decimal. We have two main ways. Actually, there are other ways, but I'm teaching these two main ways. If you are happy with one of them, use it. If you're not happy with any of them, you can learn from online resources or anywhere, or books, whatever method you like, and just stick to it. Usually in questions, I don't ask you to use only one method. I may ask you just convert it and show me your method. So it's not restricted. I usually do not do that. I don't restrict it to a certain method. So we can use the weight method. So the weight means what? Now look, we write the number like this, the way it is. So we are trying to convert this one to a decimal. This is binary. We are trying to convert it to decimal. We write it this way, the way it is. And then we list the weights. And we ignore, we ignore the zeros. We ignore the zeros. Why? I will tell you why. Now, let's list the number the way it is. 11011101. Okay, this is our number. So what are we going to do? Here, 1, the least significant, has the weight of 2 to 0. 0 has the weight to 2 to 1, and so on. List all of them. Now, in order for us to convert it to decimal, we need to multiply this by its positional weight to convert it to decimal. So 1 times 2 to 0. 2 to 0 is 1, so 1 times 1. Okay? This is this part. Or if you would like to start, you can start from here. If you like it, it's up to you. You can start from here, or you can start from here. It doesn't matter. There is no actually fixed method, unless you want just to go from left to right. If you want to consider it more organized from left to right, so you can start from here. 1 times 2 to 6 plus 1 times 2 to 5. So when you multiply 1 to anything, it's the same value. So 2 to 6 plus 2 to 5. Now 0 times 2 to 4. 0 multiplied by anything is 0, so ignore it. Then 2 plus 2 to 3 plus 2 to 1. Here is 0. Plus 2 to 0. So 2 to 6, that's 64, 2 to 5, 32, 2 to 3, that's 8, 2 to 4, that's 4, 2 to 2, that's 4, plus 1. Sum them up, you will get the decimal number, okay? The same goes to also binary point. We apply the concept of weight, but here the weight is applied in negative. So let's list our number. And remember that we have a binary point, which will be converted to a decimal point when you convert the number to decimal. So list them down. Now we start with this. This is the, in this case, the most significant in this case. So 2 to minus 1, 2 to minus 2, 2 to minus 3, 2 to minus 4. This is 0, so it will be ignored. 2 to minus 1 plus 2 to minus 3 plus 2 to minus 4. So 0.5 plus 0.125 plus 0.0625. So if you sum them up, you will get the number in decimal. And I believe it's straightforward. Sum of weights. So think about decimal to binary conversion. So for decimal, we converted binary to decimal. I gave you one method. Now for decimal to binary. Now if we would like to do the opposite, if we have a decimal, a decimal value and we would like to convert it to binary, what should we do? We have sum of weights. Sum of weights means what? You take the number, whatever the number is, and decompose it to sum of weights. It needs a bit of experience. Now the weights depend on the standard weight for binary system. Okay, what does it mean? Let's take a simple example. 9 can be decomposed to 8 plus 1. Someone may tell me it can be decomposed to 7 plus 2. Yes, but it doesn't apply to binary system. Binary system, we have the weight of 2, which is 2 to power 0. That is weight of 1. And we also have the weight of 8, which is 2 to power 3. Now, someone will say, how about why didn't you compose it, let's say 2 to power 2, 2 to power 2, 2 to power 0. Well, it applies, but it's not the right conversion. Why? You are repeating 2 to power 2, 2 to power 2 twice. You shouldn't do that. You should take the highest positional weight. So 9 can be decomposed to the highest positional weight 8 or 2 to 3 and another positional weight which is 2 to 0. Now you can list them down. Now list down the way it is: 2 to 0, 2 to 1, 2 to 2, 2 to 3. We have 2 to 0, we have 1 listed. This one we don't have, 0. This one we don't have, 0. 2 to 3 is 8. We have 1. So the final value would be 1, 0, 0, 1. I think maybe I should use some pen to explain it if maybe it's not clear. Again, what we do is we decompose the value to two parts, and these parts should match with the standard of the weight of binary system. 9 is an easy actually value. It could be also 7 or whatever, 5. Could be higher, it could be more or less, it doesn't matter. Now for this case we can say 8 plus 1. Why 1? Actually 1 has a positional weight 2 to 0. 8 also has a positional weight 2 to 3, and that is the simplest decomposition. We don't have any repetition here. So in this case, what are we going to do? We list down our weights: 2 to 0, 2 to 1, 2 to 2, 2 to 3, and then see these weights, they match with what? This is the first one. It matches with this. So list it below it. And you do the same. 2 to 1 we don't have, 0. 2 to 2 we don't have, 0. 2 to 3 we have, 8. So list 1 down. That's exactly the way. Take another example. 12. 12 can be decomposed to 8 plus 4. Or you may say, well, how about 8 plus 2 plus 2? Yes, it could be 2 plus 2 plus 2 plus 2, but that doesn't work. We need the largest decomposition of positional weights. So 8 plus 4, and in that case, think about 4 is actually 2 to 2, and 8, 2 to 3, in between, whatever in between before. Now we don't have between. 2 to 3, 2 to 2 and 2 to 3 are stuck to each other, but 2 to 1 and 2 to 0 are not there. So we have 0, 0, 1, 1. Here. I started from LSB. So it's read the correct way. It's read is 1, 1, 0, 0. So those we list down 1, 1, and then the positional weights here 0, 0. Take another one, 25. 25 can be decomposed by 16. Now how do I know? You may ask this question, how do I know by which value I start? Actually, by practice you will get used to it. The closest 2 to power n less than this value. Closest means what? 2 to power n, 2 to 4, that's 16. 2 to 5, 32. 32 is higher than this. Okay? So 2 to 4, 16 is lower than this. So our composition starts by 16. Then 16, what's lower than 16? Half of it, 8. So 16 plus 8, 24. What's left? 1. So this is the decomposition. So we have what? 2 to 4, 2 to 3, 2 to 2 we don't have. 2 to 1 we don't have, 2 to 0 we have. So 1, 1, 0, 0, 1. Why 0, 0? 2 to 4 is available, 2 to 3 is available, but 2 to 2 is not, and 2 to 1 is also not, so they are composing 0 and 0. And then the final one, 2 to 0, is composing 1. You can go on, try with rest. If you are not happy with this method, I said I will teach you another method. We have what we call the repeated division by 2. So if you're not happy with the method I just taught now, this weights method, so what are you going to do is you can try to use a repeated division. We repeat the division by 2 and take the remainder, and then it will be actually a conversion. What do I mean? Let's take a very simple example. Let's just start by 6 as a decimal number, and we would like to convert it to digital or binary. 12, not 6. 12. If we divide 12 by 2, the result is 6. Do we have any remainder? There is no. There is no remainder. 12 by 2, that's 6. So the remainder is 0. List it down, write it. 6, take it to another step. 6 divided by 2 is equal to what? 3, and there is no remainder, so the remainder is 0. Take this outcome here, list it down. 3 over 2, that is 1 with the remainder 1. Why? 3 divided by 2, so that is actually 2, or you can say, that's 1. Why? Because how many 2's in 3? Only 1. What is left as a remainder? 1 times 2, that's 2. 3 minus 2, that's 1. List it down. So we have 1. 1 divided by 2 is 0. There is no any 2 in 1. So what's the remainder? The remainder is 1 itself. So you list these down, then you twist them. You take them this direction. This one will be the least significant here, and the last one will be the most significant. So your number will be 1100. So it's listed from here, the last one to the first one. Or actually we twist them. We take this side. We twist them. So this one will be the least significant bit and the most significant bit. This one is more practical than the previous one, I guess. Or it's up to you. I mean, to me this one is more convenient. Why? Because I got used to the weights and their conversions. I can do it in a quick way. But if you like to go to the safe side and use this method, it's up to you. That's totally fine. Take another example. 19. If we divide 19 by 2, that's 9, and the remainder is 1. So 9 times 2, 18. 19 minus 18, that's the remainder 1. When you divide by 2, the remainder will be either 0 or 1. So you don't have to do this process of 9 times 2, 19 minus 9 times 2 to get the remainder. It's either 0 or 1. Okay, so 9 divided by 2, that's 4. Okay, what's the remainder? Also again 1. 4 divided by 2, that's 2, with the remainder 0. 2 divided by 2, 1, remainder 0. 1 divided by 2 is 0, with the remainder 1. And then we twist them again to get the LSB and the MSB. It will be 1, 0, 0, 1, 1, and that's the representation. Now, an easy way for you not to make any mistake, if the number is odd, then your remainder is 1, or the result of the division, or even the initial number. And if the result here of the yield is even, then the outcome, the remainder is 0, and the outcome is also even, and so on. Unless you are dividing 2 by 2. That's the only case will get you an odd number. Why 2 by 2 is 1. There is no even in this case. All right. You can apply to the next example. It's just pretty much the same concept. How about the fractions? The fractions, we do not divide by 2. Rather, we multiply by 2. We have a repetitive multiplication by 2, or we can have the weight. Okay? We can use the weights, same to this one. Here we are using weights. We can use these weights also for the decimal. So if we have a binary point and we would like to convert it to a decimal number or fraction, In that case, what we do is we set up the weights. So look at this. For example, if we have 0.625, now what can we convert it to a binary? We decompose it. Now remember that the first binary weight next to the binary point is 0.5 or 2 to minus 1. Then it is halved, then it is halved, then it is halved, and so on. So initially what we can do is we can decompose this to some, or you can say decompositions or some fractions. 0.5 plus 0.125. How do I know? Well, positional weights. 0.5, 0.125. So they compose what? Now look at what's in between. If we divide 0.5 over 2, that's 0.25, and you keep on moving. So here what do we have? This is the first positional weight. Second positional weight, 0.25 is not available, so it's 0. And the third positional weight is available, so it will be point, of course, the point here is binary, 0.101, and that's the conversion. If you're not happy with this, then what we can do, similar to the division, the repetitive division by 2, we will make the multiplication repetitive or repeated multiplication by 2, and in that case, we can get the answer based also on the carry, not the remainder. Here we don't have remainder, we have a carry. How do we do it? Let's go to example directly so that we don't waste our time. Let's take a number. Let's say we are looking for the conversion of 0.3125 to binary. We multiply it by 2. No, we divide it. This is a decimal. A binary point or a fractional binary number. We multiply it by 2. So what will happen? Just multiply it by 2. 6 to then 5. So 0.625. Okay. Do we have any carry? No. Anything comes. Carry means anything comes here. We don't have. So list it down. 0. Okay. Take the same number. Multiply it again by 2. That will be 1.25. You can multiply it. That's exactly 1.25. So we have a carry listed down here. Okay. Then strip it. Strip this binary. Strip this number. Take it. This is not binary. Strip this number. This is decimal. Take only the fraction part. 0.25. 0.25 multiplied by 2. That's 0.5. 0, you don't have to say it. You don't have to say 0.50 or 0.50. So 0.5. How about the carry? There is no. So list it down. So we don't have carry, you list it down. Same like this. Again, if you multiply this by 2, it will be 1. So only one carry. There is no any fraction. That's over. So we reach to our number. How do we read it? This is the most significant. It starts from the leftmost after the binary point, and then this one next to it, until the least significant. So 0.0101. This is the way we do it. Okay, we have an arithmetic operation for binary. Arithmetic means what? Addition, subtraction, multiplication, and division. These are the basic arithmetic operations. Why do we have them? In computer, we must have these arithmetic operations, otherwise the computer would be useless. So how do we have, or how do we apply those to binary? In decimal, they are easy. We know how to do them, but in binary, they are a bit different. So let's think about them. We have 4 rules for binary addition. 0 plus 0 as a digit is 0, and there is no carry. 0 plus 1 is 1. This is the sum, result, and the carry is 0. 1 plus 0 is 1, and the carry is also 0. 1 plus 1 is 1, 0. Okay? Or you can say 0 with 1 carried. So we have a 1 in the carry. So we have a new digit. Why positional weight? The result is 0, and there is a carried 1 to the next digit. Okay, this is the idea. All right, let's take a few examples. These are not decimal. This is not 11. It's 1 1. It's in binary or digital. This is 1 1 plus 1 1. 1 0 0 plus 1 0. This is not 100. Okay, so pay attention to that. These are binary numbers. Let's start by this one. Let's take the hardest two. This one and this one. These are the hardest. Well, we will explain about them, no problem. So 1 1 plus 1 1. 1 plus 1 is 0 with 1 carried. Okay, carry this one to the next level or the next higher level, higher weight. 1 plus 1 is 0 with 1 carried. So we have 1 carried here. Still we haven't yet done. 0 plus 1, why? 1 plus 1 is 0, the result is 0 up to here, and 1 carried, so we place this one here. We wait for the result, we have 1. So 0 plus 1, that's 1. With 1 carried, we don't have any number here, drop the 1 down. So it will be 1, 1, 0. Again, in order for us to understand it, okay? 1 plus 1 is 0 with 1 carried. So we have 1 to be carried to the next level. Okay? So we have 1 carried plus 1 here. That is also 0. And with 1 carried. So we carry the 1, we put it here, place it here, and wait for it. Wait, we haven't yet done because we have 3. So 1 plus 1 is 0. Plus 1 is 1. And we have 1 carried. 1 carried here, we don't have any digit, drop it down. Let's take this one, this is easy. 0 plus 0 is 0, clear. 0 plus 1 is 1. 1 here, we don't have any digit, drop it down, or you can say 1 plus 0, it doesn't matter here. The leftmost, 0, it doesn't matter also in binary, okay? For the time being. Later on we'll explain about it. Let's take this one is harder. This one is the representation in decimal. So if you want to go through it, okay? 1 plus 1, that's a 0 with 1 carried. So list this one here. 1 plus 1 is 0 with 1 carried. 0 plus 1 is 1. So 1 plus 1 is 0, listed down with 1 carried. So 1 here is left with no any digit to be added, it will just be dropped down. So 1 0 1 0. And you can apply the same concept to all other questions. It's not really hard. For the binary subtraction, we have 4 basic rules. 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, and we cannot say 0 minus 1. Actually, we need to borrow. Why? 0 is less than 1, and in binary, in order for us to make a correct subtraction, we need to borrow 1. So it will be 1 0 minus 1, that's 1 with a borrow 1. No, there is no carry here, a borrow. So we borrow 1 from the next positional weight. Okay? I repeatedly get this question, from where do you borrow? You don't have to worry about it, it's not money. You just borrow from the next level or the next positional weight. Okay? Let's say we don't have, no problem. You can say it is 1 with 1 borrowed. Borrowed from where? You don't have to worry about it. You're not going to pay for it, so don't worry about it, okay? Okay? Let's move. Let's take some examples. 1, 1 minus 0, 1. This is easy. List them down in column format. So 1 minus 1, that's 0. 1 minus 0, that's 1. So this is simple, straightforward. Let's take 1, 1 minus 1, 0. 1, 1 minus 1, 0 is also simple, actually straightforward. This one has no much of a difference. 1 minus 0, that's 1. 1 minus 1, that's 0. You don't have even to write it. It doesn't matter. Okay. Let's take this one, it's a bit harder. 1 minus 1, that's a 0. 0 minus 1, we can't say it. We need to borrow. So 1, 0 minus 1, that's 1. So we borrowed 1, this one is cancelled. So we don't have anything here. You just list down these 0 or you even cancel it, it doesn't matter. It depends on the type of the representation, because we may represent a number, a binary number in 3 digits, in 4 digits, in 5 digits. So if you want to represent, let's say, in 8 digits, even if these are zeros, you need to write them. And we will reach to that part. But for the time being, this one is irrelevant. It's exactly like I say, instead of saying, let's say 90 in decimal, I say 0, okay, 90. It doesn't make sense, right? So in that case, we just say directly it's 90, right? But we don't have to say 090. This one is not read. But in digital, it is read 010, and it depends on your representation. If you are going to 2-bit, 3-bit representation, 4-bit, it doesn't matter. We will explain about it later on. Okay. Binary multiplication, again, we have 4 basic rules. 0 times 0 in digital here, or in binary, not in decimal, is equal to 0. 0 times 1 is also 0. 1 times 0 is also 0. 1 times 1 is 1. So it's always 0, except when they are both equal to 1. And that can be represented easily in digital circuit, and explain about it in, a while, after a few chapters. Let's take some examples. This is not 11 again, it's 1, 1 times 1, 1. So 1, 1 times 1, 1, we go based on partial products. Partial products means what? Now we start by 1. 1 times 1, 1 is exactly 1, 1. 1 times 1 is 1, 1 times 1 is 1. You list them down. Now when you go to the positional weight here, you shift. Why? Because it depends on its own weight. This has a different weight, higher than this, so you shift and you list down. So 1 times 1 is 1. You start writing from the positional weight here. Okay, 1. So 1 times 1 is also 1. So now you sum up these partial products. Sum them up means what? 1 plus here, we don't have any 0. So it will be 1 plus 0. 1 plus 1 is 0 with 1 carried. 1 plus 1, so we have 1 carried here. 1 plus 1 is also 0 with 1 carried again. So 1 carried, 1 drop it down, or just say 1 plus 0 is equal to 1. So it will be 1, 0, 0, 1. I will repeat it again. It depends on the partial products. Partial products means what? Similar to the decimal multiplication. We go 1 by 1. So 1 times 1, that's 1. Remember, its positional weight is here, so you start from here. 1 times 1 is also 1. Leave it, go to the next positional weight. 1 times 1 is 1. Start from its own positional weight here. 1 times 1 is 1. Now sum the partial products. These are called partial products. 1 plus 0, we don't have any digit here. So 1 plus 0, that's 1. 1 plus 1 is 0 with 1 carried. So list it down. 1 plus 1 is 0 with 1 carried. So we have 1 plus here 0, so 1, 0, 0, 1. Let's take another example. Maybe it's a bit vague until now. We have 3 partial products. Why 3 digits? So 3 levels. 1 times 1 is 1, 1 times 1 is 1, 1 times 1 is 1, so 1, 1, 1. It will be the same. 0 times 1 times 1 times 1 is 0, so list it down starting from its own weight. So 0, 0, 0. 1 again. 1 times the same number, it will be the same number. Start from its own positional weight. Look, same positional weight. Okay, here. So 1, 0, sorry, 1, 1, 1. Now sum up. 1 will be dropped. 1 plus 0 is 1. 1 plus 0 is 1. Plus 0 is 0 with 1 carried. So 1 plus 0 is 1. Plus 1 is 0 with 1 carried. 1 plus 1 is 0 with 1 carried. 1 plus nothing here would be just dropped down, and that's the answer. I hope it's clear. Let's move on. Binary division. Binary division is a bit of a special case, okay? And it applies in a similar way to the decimal division. What does it mean? Let's say we are dividing 110 by 11. So what do? We list it down like the division procedure. 110 divided by 11. So in order for us to start, this is 2 digit. Do not waste your time. 0 divided by 11, it's 0. 10 divided by 11 is also 0 because it's less than 11. So if the 2 digits are not equal, okay, or more, then do not divide. You just go directly to the higher level. Higher level means what? In order for us to divide, in this case, we take the whole piece of a number. 110, we divide it by 1. So what are we going to get? 1. It's either 0 or 1, okay? So 1, multiply this 1 times 1 and list it down here, starting from the same level. So 1 times 1, it would be 1, subtract. Subtract what? 1 minus 1 is 0, 1 minus 1 is 0, 0 minus also 0 is 0. So that's it. It would be 1, 0. Be 1, 0. Why 0 here? The final result is 0. If you divide it by 11 is 0, just list it down and that's it. Let's take another example. Maybe it's a bit vague until now. Take another example. Maybe it will be easier for you to catch the point. Now look at this example. We have 110, the same number divided by 10. It's a bit different. Now look, there is no point to start from 0. Why 1 digit divided by 2 digit? No point. We go to 2 digit, 10. So 10 divided by 10, that's 1. Okay. Multiply 1 times 10, that's 10, list it down. Okay. So list it down, subtract. If you subtract in this case, what are you going to get? Well, 0, then 1, 0 drop down. So this one will be cancelled with this. And then 1 minus 0, that's 1. 0 minus, actually nothing, is 1. So 1, 0. 1, 0 divided by 1, 0 is exactly 1. Multiply 1 times 1, 0. That's 1, 0. Subtract. 1 minus 1 is 0. 0 minus 0 is 0. That's it. You're done. Okay? So this is the idea in this case. You may say, why did you say we have 0 here? Previously we added 0 here, but we didn't add here. Because we still have a digit to be divided. And dividing a digit by 2 digits is 0, because it's less than it. So if you divide 0, no need 0. 1, 0 by 1, 1, that's a 0. With some remainder, yes. Because it is lower than it or less than it. Okay. Let's move on. This is a very important topic, the ones complement and twos complement. Ones complement is found actually for some purposes. First of them is calculating the negative numbers, and for some other applications of inversion. So the ones complement is what? You take a binary number, you invert each one to 0 and each 0 to 1. So any binary number you have like this, what you need to do is you need to consider each 0 and convert it to 1 and each 1 to 0. That's ones complement. Finish. How do I do it? In digital circuits or logic circuits, how can we convert 0 to 1? We can use NOT gate. NOT converts 0 to 1 or 1 to 0. Okay? So if we apply in parallel whatever inputs we have to NOT gates, we will get the ones complement and the output. The twos complement, actually we add 1 to the ones complement of the binary number. So if we want to calculate the twos complement of a binary number, what we are going to do is we get first the ones complement of that binary number. How do we get it? We change each 0, we convert the 0 to 1, all zeros to ones and all ones to zeros. Then we add 1 to the resulting number. Let's try to do it. Let's say we have this number and we want to convert it to twos complement. Now initially this number is 1, 0, 1, 1, 0, 0, 1, 0. Convert the zeros to ones and ones to zeros. So it will be 0, 1, 0, 0, 1, 1, 0, 1. Add 1 to it. So this is ones complement. I'm not interested in it. I'm interested in twos complement. So add 1 to it. In order for us to get the twos complement, add 1. So 1 plus 1, that's the 0 with 1 carried. 1 plus 0, that is 1. So we have a new number will be the same, 0, 1, 0, 0, 1, 1, 1, 0. So only change of these two digits. But this is the twos complement. We add 1 to the ones complement of the binary number, and we get 2's complement. There is another way to do it. In order for you to calculate the 2's complement directly without going through the ones complement, you can take the binary number and go through it until you reach to the first one. What does it mean? From the right side of the least significant bit. Okay, so you start from the right side or the least significant bit. This is LSB. You start checking until you reach to the first one. It may be the first one. Maybe this one will be 1. Once you reach to that one, keep that one aside. Okay, keep those aside. You reach to this part. Now we checked 0, 0, 0. We got 1. Okay, this one. Keep it in one group. Then go to the next part. Convert each 1 to 0 and each 0 to 1. Take the ones complement of the rest. So what does it mean? It means, now look at this number. 0, 0, 0, I haven't yet reached 1. 1, okay, I reached. We move from the least significant bit, remember, not the most significant. So we reached to 1. Take this one as a part, one part, don't change anything in it. Next to it, change each 1 to 0. So this one will be 0, this one will be 0, this one will, each 0 to 1. This one will be 1, this one will be 0. And that's it. So you take the ones complement of the second part. How do we create 2's complement in logic circuit? We take the ones complement, so it's a NOT gate or multiple NOT gates. Then we add one bit to it. How do we add a bit? We can use an adder, and that will do for us. This is the end of this part of the chapter. I'll create another part very soon. Until then, have a good time. Goodbye.